Hi there, are we online? Let's see, here's my slides. Alright, so this is a draft recording of a talk that I will give next week at the Bernoulli Center. It's aimed at sophisticated math audience, so I will mention some mathematical terms that I will not explain, like local systems, extended TQFTs. So this is for people who sort of know this already. But maybe you can still get something from it if you haven't heard these terms. I'm not sure. Alright, so here we go. So it's called TQFTs of higher supergravity gauge sectors. It's based on material that you find in these texts here. The character map in non-abelian cohomology is a monograph we wrote a while back. Complete topological quantization of high gauge fields, high gauge theory and differential non-abelian cohomology, and higher superspace supergravity and its IR completions. Alright, so we'll be talking about what I call IR completing of higher gauge fields. So this has to do with the fact that quantum field theories are traditionally defined incrementally. This is kind of admitted after the fact by terminology such as speaking of a UV completion. So you start with some theory and then you say, oh, it's not complete yet. Not UV complete, for instance, then you go about UV completing it. So this is about the local interactions, what happens in tiny regions. This has received quite a bit of attention, at least people talk about it. It's hard usually, or regarded as hard, to find UV completed theories. It's meant to be a big deal, but at least as a problem, as an issue, it's well known. Less widely appreciated as a concept already is the kind of opposite completion, what I would call IR completion, the infrared completion, which is the completion of the field theory at long distances, the specification of the global field topology. So this involves what is known as flux quantization, if there's high gauge fields with higher flux densities, and it characterizes the brane charges, the higher dimensional analogs of monopole charges in your theory. And I want to briefly highlight here one way of thinking about this global completion. So if we are dealing with a high gauge theory, there's some gauge field, which I'm denoting abstractly by hat A here, and locally on charts it's given by some differential form data. The actual gauge potential is shown here as A. So this lives on some open cover of space-time, hence locally on charts. And in 99.99% of the literature, of the physics literature, this is actually all that is ever considered. But this is only the local gauge field content. In order to globally define your theory on spacetimes beyond a single chart, where non-trivial topology may kick in, we next need to glue these gauge potentials on overlapping charts by gauge transformations. These gauge transformations in turn need to glue by gauge of gauge transformations if we're in a higher gauge theory on triple intersections of charts and so forth. So there's in general an infinite tower. It will in practice truncate at some stage of high data that is all part of the field content actually. And specifying that is what I mean by IR completion here. So the IR completion is particularly necessary in order to get the topological sector, the TQFT sector of your theory. Once you have the IR completion, you can ask what are the topological charges, what are the topological observables, and you can ask for the dynamics of just these. That would be the topological sector of the theory, and under good conditions, and we'll touch on this later, they will form a field theory by themselves, the topological sector TQFT. So this is very much a non-perturbative issue here, which in general hasn't received that much attention. Non-perturbative physics, by and large, is yet to be discovered, and part of what I'm talking about here is how to actually do these IR completions for the higher gauge sectors that appear in particular in higher supergravity theories, like notably 11-dimensional supergravity and its dimensional descendants. This is quite in contrast to most other discussion of completions of field theories, non-perturbative. Alright, so before we come to kind of the actual content, I'll step back and recall, for those of you who know this, what I'm saying now is well known, but we'll see in a second that you may not actually have seen this before, even though the experts know this. But anyway, so I'm recalling this IR completion of Maxwell theory, by which I mean, for a second, let's look at ordinary vacuum electromagnetism on globally hyperbolic 4D space-time. So there's Lorentz manifolds of the form R1, the time axis, times x3, where x3 is a 3 manifold that goes by the name Cauchy surface or Cauchy hypersurface, really. So we're dealing with a theory that has, on space-time at least, single flux density F2, the electric magnetic flux density, and away from monopole sources that are indicated in this graphics on the left, it's controlled by the Gauss law, dF2 equals 0. topologically. So then one can compute the phase space of this theory, meaning the symplectic manifold with canonical coordinates and canonical momenta that describes the initial value data on X3 on the Cauchy surface for on-shell solutions of this theory. And if you open textbooks, articles on what this Cauchy surface is, and no Teitelbaum or something, you will get the following naive answer. It's not the correct answer globally, but it's the correct local answer. So it says the canonical coordinate is the gauge potential, which people will write down as a one form, often actually without even specifying where this one form exists. But if we are naive, it's assumed to exist on the whole Cauchy surface. So it's a one form. Omega 1 is my notation for one forms here on X3. And if we go to the reduced phase space, it's modulo exact forms. And the canonical momentum is the electric field. So this one form on X3 should be thought of as being just the potential for the magnetic flux in temporal gauge, actually. And the canonical electric momentum, the electric flux is the canonical momentum for that, a two form. So that is the naive description. This is not actually true in general. In general, the electromagnetic field is only locally given by one form. Globally, there's more data. So the infrared completion of ordinary Maxwell theory that goes back to Dirac's famous article from 1931 on singularities in the electromagnetic field, in modern paraphrase, Dirac didn't say it that way, but one can see the roots of this idea in his article, is that the actual canonical coordinate is we put a hat on this A1 to indicate that it's something richer, namely it's a co-cycle, or if we go to the reduced phase space, a cohomology class in the ordinary differential cohomology in degree 2 of X3. And I'll recall what that means in a moment, but in words it means that that A1 is, for instance, a connection on a U1 principal bundle, or it's a Shiga-Simons character of degree 2, or it's a zero gerb, or whatever with connection, whatever you want to call it, differential cohomology class. And in that vein, it's good to write E2, even though it's the same. E2 doesn't change in this picture here in Dirac charge quantization. It's only the magnetic charge in flux that is quantized. The electric charge is left untouched. But just to indicate how it fits on the same footing here, we can understand that this closed 2 form is also equivalently a cohomology class in the differential R-valued cohomology. Differential cohomology with coefficients in R is actually isomorphic to just closed 2 forms. So this is what most sophisticated modern textbooks, or the handful of modern textbooks, will say. Berlinski, for instance, on loop spaces and geometric quantization says it this way, up to notation, of course. But that's actually still not the full story. So you could ask, well, why didn't we do anything to the electric flux here? Why just? Because we didn't. We just changed the notation so far. And in fact, you can. If you worry about duality symmetry between electric and magnetic charges, then the previous line is unsatisfactory, because the magnetic flux lives in a different cohomology theory, according to Dirac, than the electric flux does. So to rectify this, you can postulate that no, also the electric flux should be quantized as the differential co-cycles with integer coefficients. So it should also be, if you wish, a connection on a principal U1 bundle. So in that situation, we would have the symmetric situation. There's a white hat A1 and a white hat prime, and they're both co-cycles in differential cohomology in degree 2. They're independent because we are on, this is important to remember, to recall, because we are on the Cauchy surface. So as you time evolve these, you will have to use the Hodge star on the ambient space-time to see that they actually that one of these is actually the extension of one of these to space-time is actually the Hodge tool of the other. So this is, but on the Cauchy surface they become independent. And the point I want to highlight is that this is not the end of the story. So far this is known. There's a handful of authors who consider this. Friedmo Siegel, for instance, have considered, or maybe the first, this duality symmetric IR completion, but then other authors too recently. Carlos Shabazi, for instance, and Kalan Lazario have discussed it this way for the supergravity. But one can go further. There's still nobody forces you to choose this flux quantization condition. In general, I claim, and I will explain this, you can choose the pair. You don't distinguish actually between electric and magnetic. You say together, I'm still writing it as a pair here, but it just says together they're a single co-cycle, in what I call differential non-abelian cohomology with coefficients in a space A, in a classifying space calligraphic A here, which is constrained in the form that its R rationalization, its realification is this Eilenberg-MacLane space B2R2. So I'm not going to explain this here. You're expected to know what an Eilenberg-MacLane space is if you're listening here. So I claim this is actually the general answer, and all the previous choices here, at least the previous two lines, are special cases of that. And what this talk is really about is this generalization to differential non-abelian cohomology, which then applies to more general field theories than just ordinary Maxwell theory. All right, so let's have a look at this. What is differential cohomology? So the first part here is well known, even though the presentation I'm giving here, the very slick, neat, transparent presentation, is not readily, I mean, some authors, there's a couple of authors again, another couple of authors that do write it this way, but I don't think this is widely appreciated. Anyway, it's true, and once you know how these things work, it's easily checked. That ordinary differential cohomology, here shown with integer coefficients, you can regard this for slightly more general abelian groups, is the sheaf cohomology, H0 of X of your manifold, of your spacetime or Cauchy surface manifold, with coefficients in this chain complex of abelian groups that write Z square brackets n subscript diff, which is the homotopy fiber product. That's my definition of this diff subscript. The homotopy fiber product is shown here of the sheaf of closed differential forms, that's our flux densities, with the sheaf of chain complexes concentrated in degree n on the integers over the analogous chain complex concentrated in degree r. So that fiber product, if you work it out, that gives you the Deligne complex. That homotopy fiber product gives the Deligne complex, and so we're equivalently saying here that differential cohomology is represented by Čech-Deligne cohomology, for instance, on ordinary manifolds certainly. And I'm claiming, this is the content of this book I mentioned, the character map in non-abelian cohomology, section 9 there, that this has a non-abelian generalization if we think of this Z mod n, this Z square bracket n, the n-shifted copy of the integers that we saw in the previous line, as being the chain model, the chain complex model of BNZ, of the Eilenberg-MacLane space BNZ, KZN. Then I'm claiming we can replace this by essentially any other space, up to some slight technical conditions, any other space A, regarded as a classifying space. If we also replace the sheaf of closed forms by the sheaf that I call the sheaf of closed L-infinity algebra valued forms with coefficients in this L-infinity algebra that I write Fraktur L of A. So by this I mean the following. So A is a space, a topological space, here addressed as a classifying space, and the simple condition that we assume is that it's nilpotent of Q finite. So people who know about rational homotopy theory will immediately know what's going on here. I'm assuming there's a good, very good notion of rational homotopy theory for this thing. This is not actually too important. The finite type condition is actually important for what I'm doing. So let me just move something here. And this Fraktur, Fract LA, by this I mean what I call the Whitehead L-infinity algebra of A. So that is the thing whose Chevalier-Eilenberg algebra is the minimal Sullivan model of A, and as such it's widely known. It seems not to be as widely known that, dualizing back, the corresponding L-infinity algebra is the L-infinity algebra whose binary bracket is the Whitehead bracket on the realified homotopy groups of the loop space of A. The higher brackets are the higher Whitehead brackets. That's why I'm calling it the Whitehead bracket L-infinity algebra. But actually in computations it's used here as the dual of this minimal Sullivan model. It's still good to understand it in this non-dual incarnation that gives the more direct picture that allows us to form this above homotopy fiber product, which I'll show in slightly more detail in just a moment. So this is what we call non-abelian differential cohomology with coefficients in any space, essentially any space. So let's see how we can use this to do infrared completions of more general high gauge theories that are called higher Maxwell type theories. It's not the most general notion of high gauge theory that you might want to discuss. For instance, it excludes the gauge field content of heterotic supergravity, but it includes 11-dimensional supergravity and all its dimensional descendants. It also includes 5D supergravity, the gauge sectors, and so forth. Alright, so by a high gauge theory of Maxwell type, I shall mean there is a what I call a characteristic L-infinity algebra. So I'm saying, okay, I call it such if we can find an L-infinity algebra to be called fructor A, little a, such that the following condition holds. So this may seem a mouthful, but it's not actually, this is actually very simple if you think about it for a second. Such that its on-shell fluxes, or rather the temporal germs of these, this is just a technical condition for solving PDEs, on a globally hyperbolic spacetime with the Cauchy surface, now of dimension d, is such that the on-shell fluxes are actually isomorphic, and we'll see this in examples in just a second if this seems mysterious. The examples will clarify it in just a moment. But the abstract statement is that the on-shell fluxes are isomorphic, the set of on-shell fluxes is isomorphic to the closed L-infinity algebra valued forms, by which I mean flat forms or Morra-Cartan elements, whatever word you want to use for speaking about the closure conditions on L-infinity algebra valued 1 forms on the Cauchy surface. Right, so let me say this again. I say high gauge theories of high Maxwell type, if its solution space on a Cauchy surface is actually isomorphic to closed differential forms, but with coefficients in an L-infinity algebra. So here's the examples. Ordinary Foddy Maxwell theory that we saw before has these simple Gauss laws, and if you think about them as differential equations on abstract algebraic elements, you'll see these are the equations on the Sullivan model for the space B2, Z2, the Eilenberg-McLean space K, Z2, 2. So that would be the previous case, and in that case for the L-infinity algebra of this is just an ordinary Lie algebra shifted in degree. And if you plug that into this fiber product formula, you just get back the Deligne complex. But now we can apply this to more general spaces and more general theories. And here just to highlight that we are dealing with both the magnetic and the electric fluxes, which is why our classifying space actually has these two copies. Remember, we highlighted this before. This has long been ignored, but it's just the fact that it's there, and we can and should discuss it. Magnetic and electric fluxes and the quantization. Alright, so now let's look at a slight generalization. There's in 5 dimensions. You can write in what's called Maxwell transimers theory. On a Cauchy surface, it has still a 2-form flux as ordinary Maxwell theory has, but now it's what in spacetime is its Hodge dual, which on the Cauchy surface becomes the electric flux density of 3-form G3. It's not closed anymore, but its differential is actually the square of the 2-form flux. And so this characterizes solutions on the Cauchy surface. And if you ask what is the L-infinity algebra such that these solutions are equivalently closed differential L-infinity algebra valued forms, that L-infinity algebra is the Whitehead L-infinity algebra of the 2-sphere. I claim, again, experts will immediately know this. I'm not going to further explain this here. This is a fact from rational homotopy theory. So an interesting different space appears, the 2-sphere. Another historically interesting case is what you could call in 10 dimensions, the type 2A supergravity gauge sector of NS-RR fields. And I should say this is actually an idealized form. This is not actually the true 10D field content. This is not what you get from 11D actually. But this is what people consider, and it has a closed 3 form, and it has this tower of 2 forms, the RR flux densities, which are in general not closed, but whose differential is that 3 form wedged with the corresponding degree of these RR forms. Again, you can look at these equations and ask, well, what is the L-infinity algebra such that closed forms with values in it are exactly these equations here. And you find it's the L-infinity algebra, which is the Whitehead L-infinity algebra of the space that goes by this name here, KU0 homotopy quotient of BU1, which is the classifying space of twisted K theory, of degree 3 twisted K theory. So this is really where, this is in paraphrase of course, modernized paraphrase I might say, this is where the conjecture comes from that RR fluxes are quantized in K theory and string theory. It comes from this, it's a reflection of this mathematical fact, or conjecture based on this mathematical fact that I'm stating. So what I'm stating here are not conjectures or anything, right? It's just truths. We're just taking the Bianchi identities here, these higher flux densities, and asking what is the L-infinity algebra that characterizes them. And these happen to be Whitehead L-infinity algebras of certain spaces. And finally, In 11D, there's an example that is structurally entirely analogous to the 5D Maxwell-Chern-Simons case, hence called the 11D Maxwell-Chern-Simons case, but degree shifted. What used to be a 2 form is now a closed 4 form. What used to be a 3 form is now a 7 form, which is not closed, but whose differential is the square of the 4 form. And by the pattern of the rational multiple types of even-dimensional spheres, the corresponding the characteristic L-infinity algebra here is the Whitehead L-infinity algebra of the 4 sphere. So these are examples of higher gauge theories of Maxwell type that appear, so the examples shown here appear as gauge sectors of high dimensional supergravity theories. We're starting in 4 dimensions, 5 and so forth. Okay, so now we can do something. Let's put it this way. Now that we have identified, by the definition and the examples we've seen, and now that we've identified these Bianchi identities with closed L-infinity algebra valid differential forms, we can very naturally actually find the IR completion if we remember that exactly these closed differential L-infinity algebra valid forms also appeared in our definition of differential non-abelian cohomology. So, for the IR completion, choose now a space, a classifying space A, such that its Whitehead L-infinity algebra is the given characteristic. So the idea is, suppose we start with a field theory defined just on the level of the flux densities, kind of 1850s style Maxwell theory, equations of motion just on the flux densities, and we're now asking what is the actual global field content of which these flux densities are the field strengths. What is the actual local field content? What are the gauge potentials? What is their gluing data? What is their global flux quantization and charge structure? And so to start with, we need to connect that classifying space to our characteristics. So we ask that for some classifying space such that its Whitehead L-infinity algebra is the given characteristic. And there are many of these in general, always. I mean, there's actually always an infinitude of classifying spaces for a fixed characteristic L-infinity algebra. You have to choose one, and that choice is extra data that is part of actually completing your theory. It's part of specifying your theory. Like the Gauss law equations were the dynamical part. Now to complete the theory, we have to make more choices, to define more of a theory. That's kind of the basic punchline that I'm trying to convey here, that most field theories that people have addressed as such are not actually field theories, yet more data has to be specified before they can become field theories globally. Alright, so if we leave that first argument of the forms open here, then we're looking at the sheaf of such closed forms, the smooth set, if you wish, the sheaf on the side of smooth manifolds. So all this actually lives in the infinity topos of smooth infinity groupoids, being the infinity sheaves on the side of smooth manifolds. That's where all these diagrams, everything lives there. So then the flux densities are actually, so the sheaf is now actually the classifying object for such closed fluxes, satisfying the Bianchi identities. So on-shell fluxes are now equivalently maps in our infinity topos from the Cauchy surface to that sheaf, called VEC-F here, indicating that one such form is actually, since the L-infinity algebra has many components, is a whole set of components of forms, as we've seen. So these are the fluxes. And now, rational homotopy theory gives us two maps. So, right, the idea is of flux quantization, of globalization, we somehow need to relate these fluxes to charges, which are in some cohomology theory. The cohomology theory is that which is going to have A as its classifying space, and so we need to somehow bring the classifying sheaf of flux densities on the same footing into a context where it sits on the same footing as this space, so that we can relate the two. And rational homotopy theory provides us these maps to the R rationalization AR of our space, the realification of our space. So first, there's the vertical map here, the R rationalization map, which essentially uniquely approximates A by its R rationalization. But there's also, if you use the fundamental theorem of the G-algebraic rational homotopy theory, there's actually this map here, the horizontal map, which can be thought of as classifying the de Rham map from that sense forms in sort of non-abelian de Rham co-cycles to their non-abelian de Rham cohomology class. So this is in section 6, this non-abelian de Rham theorem and non-abelian de Rham theory is section 6, I think, of our monograph the character map in non-abelian cohomology. But it's analogous to the abelian case, so you're meant to be kind of guessing what it's actually like. And so now that these things have been connected, we can now ask for the flux quantization of our fluxes. Namely, we say for the fluxes to be quantized, somehow they have to be the image of actual charges in A cohomology, not just in AR cohomology, not just really, but integrally. And so naively we can ask, okay, we have to make this diagram commute. There has to be a charge classified by this map chi here from space-time or from the Cauchy surface to A, such that the charges coincide with the fluxes as much as they can, namely in real cohomology. So that would be flux quantization, but of course we're in homotopy theory here. In such a diagram, it makes no sense to ask that it commutes on the nose. It can commute up to a specified homotopy. So we should really ask there to be a homotopy between the charges and the fluxes, but that is not just an existence statement, it's not just a property in general. This is extra data. And that data, as the notation already indicates, turns out to be equivalently the gauge potential. That's actually where the full field content sits. That homotopy, if you work it out, that is implicit actually in this previous homotopy fiber product description of the de-link complex that I mentioned. That homotopy is where the gauge potentials sit. And so that is the full field content now, the infrared completed field content. The statement here is, just by choosing the space A, subject to the condition that its weighted L infinity algebra is the characteristic of our fluxes, the onshell flux, that specifies the field content. The globally defined fields are such diagrams, and we can make this a bit more explicit, or a bit more, pronounced, by noticing that we've been building a cone here over this cospan over AR. So by the universal property of its homotopy pullback, which I call a diff, it's a smooth infinity group mode, or smooth infinity stack, which is the homotopy fiber product of the differential forms with the classifying space A. We've seen this before. This is the coefficient of our differential non-abelian cohomology, and by the universal property of the pullback, we're saying that the global field content is equivalently a map, now shown as a dashed blue map here, from the Cauchy surface to that coefficient object. So that is what IR completion of high gauge fields means. So once we have that, once we've chosen A and thereby R completed our field theory, we can now do field theory. We can work out stuff. For instance, we can find the phase space of the theory. So we've just seen it's kind of just a rewording of what I just showed. We've seen that single field configuration is a map from Cauchy surface XD into a diff, the coefficient infinity stack, moduli stack of differential A cohomology. And so the space of all fields, of all on-shell fields, by the way, the on-shell condition is all on-shell. It's all built into the fact that these curvature forms here are closed, right? So that means the whole on-shell space should be the space of all the maps, so the mapping space or the mapping stack from XD to A diff. So this is, if you should think of it being the stack, the space of differential cocycles of IR completed fields modulo gauge symmetries, high gauge symmetries, and so forth. And now we can consider its shape, and by the shape I mean the underlying homotopy type. Sometimes it's equivalent to the path infinity group, or known as the topological realization of this stack, of this phase space stack. And technically it's the left adjoint construction to the full inclusion of plane infinity group modes into smooth infinity group modes. So that shape, I claim, is just a mapping space from the manifold XD to A. So you see the diff goes away. So as you go to the shape, you just see the that's why it's called shape. You see the global shape of this phase space, not what it's locally like, but the differential refinement was just about this local behavior, and so we get this mapping space. And we'll see this is the brane charges modulo global symmetries. So pi zero of this, we'll see this pi zero of this is the A cohomology of XD. That is the charges of the theory, coefficients in A, the homotopy class of charges, and as a space, it's these charges modulo global symmetries, namely modulo, right? So we started with just gauge symmetries. We've done away with all the local gauge transformations. We just kept the globally non-trivial part of the gauge transformations, and those are the global gauge transformations. And I'll say in a moment why I call this the black or the singular brane charges, because there's other brane charges, there's the solitonic ones, which we come to now. So all the previous story has actually an analog, which I haven't shown, but which I'll just trust you can believe exists. The solitonic version where we do all the previous constructions, but impose compact support both on the fluxes and the charges. And once you do that, so this is the condition that fields vanish at infinity, or field strengths actually vanish at infinity, physical condition. And if you do that, then by cohesion, by the fact that smooth infinity groups form a cohesive infinity topos, by some technical yoga, one finds, well, it's the same yoga as before actually, I mentioned it already, I think. One finds that the shape of the solitonic phase space, of solitonic fields, those that vanish at infinity, is actually the pointed mapping space out of the one-point compactification of our Cauchy surface, which physically you should think of as adjoining the point at infinity. So we literally adjoin the point at infinity to our spacetime, and then we ask that we have a pointed map so that it sends infinity. So A is pointed by 0, and XD is pointed by infinity. So we're asking that literally the charges take the value 0 at infinity. That is the remnant of the compact support condition. And so this we should think of now as being all brane charges, not just the black or singular ones, modular global symmetries. And what this means is that on top of the monopoles and the high dimensional generalizations, we now have what you might call what in electromagnetism are the vortices. Right? So these are the two kinds of branes in ordinary 4D electromagnetism. There's the singular branes that everybody talks about, is the magnetic Dirac monopoles that are hypothetical. They are sources of flux lines. Flux emanates from them. But there's actually also solitonic branes that are actually, in contrast to the Dirac monopoles, that are actually observed in experiments since the 1960s. They are Brikosov vortices. If you send magnetic flux through a type 2 superconductor, it will pinch through these compressed flux tubes. The flux lines will pinch through that. And the mathematics underlying this is the condition that flux has to vanish at infinity. It has to be localized on the superconductor. And so the solitonic condition brings in these solitonic branes. So that's why we have now all branes. Alright, so with the phase space we have access to the observables. Observables of any field theory are just smooth functions, values in the complex number say, on phase space. They're just functions on phase space. And so here's just a map from our phase space stack to C. And since C is actually, it's a zero truncated infinity stack, so that actually makes these things automatically be gauge invariant by the yoga of the localization of infinite toposes. So these are actually the right observables, just these maps here from phase space. And we'll be focusing, as I indicated at the beginning, we'll be focused on the topological observable. So we want to call an observable topological if it's independent, of course, of local variations of the fields, and just depends on what the fields do globally. And we can easily do this now because we have this shape of the phase space, which was exactly kind of that aspect of it that remembers only these global properties. And there's a canonical map from the phase space to its shape, the unit of the shape modality. And so we say that an observable is topological if it factors through this unit. So if it's a map, if it's a function actually on the shape of phase space, and as such it becomes a function on all of phase space, which however is independent of the non-topological data. So that's a topological observable. And then we should just admit that if we're really talking about actual observations and actual laboratory physics, then the realistic observations that we will actually be able to do are completely supported, because our measurement apparatus will be finite, so we'll not be able to really probe sort of a non-compact and infinitely extended part of phase space. So that's an evident condition on actually realistic observables, and the upshot then is that the realistic topological solitonic observables of our infrared complete high gauge theory are just the homology of the shape of the solitonic phase space, right? So we're talking about, if we're just looking at these functions to C here, talking about compactly supported functions on this space by the fact again that C is zero truncated. These are actually functions just on the connected components pi 0 of the shape, and they're compactly supported So they actually take values on a finite number of them. So they're homology classes in H0, and by the same logic, you can now speak about the higher observables being the higher homology. They observe these higher global symmetries, or generalized symmetries, as people like to say these days. So the topological observables are just the homology of the solitonic phase space, which is really just a pointed mapping space. The co-cycle space, if you wish, of our A cohomology, or reduced A cohomology. Right? So that's something we just learned from just thinking carefully about what it actually means to do an IR completion for high gauge theory. Okay, so here's a remark which I'll skip. Now let's look at spacetimes that have a yet more special form. We have been looking at globally hyperbolic spacetimes of the form time axis times the Cauchy surface. Let's assume we can actually split off one more R factor. Let's look at spacetimes of the form R1, 1 times x times a d minus a one-dimensional space. So we can kind of split off a two-dimensional Minkowski spacetime, which you can consider light cone propagation. Hence, equivalently, we assume that our Cauchy surface xd splits off a factor of R1, which we going to think of as being kind of part of the longitudinal axis along which light cone propagation of this spacetime will take place. But anyway, whatever you think about it, it's a mathematical fact that in this case the solitonic topological observables are, in the sense that they naturally carry a star algebra structure called the Pontryagin product. Namely, topological observables, remember, was these pointed maps from the one-point compactification of the Cauchy surface to A, but the one-point compactification of such a product is a smash product of the one-point compactifications of the two factors. So it's a smash of a circle with the compactification at x d minus 1. You can take that circle out, and you find that this mapping space is equivalent to the loop space of the mapping space out of this lower dimensional thing. And in degree 0, which I'm showing here, this H0, which is with its Pontryagin product structure, is just a group algebra of the fundamental group of the mapping space. So I'm not sure if this helps anybody, but I thought I'd draw this at some point. So this product we're looking at, so the observables, the observables on something like integrated flux densities. This is a kind of an impressionistic idea of what we're looking at here. I just want to illustrate that the product in this algebra of observables that we just found is kind of a light front ordered product. So if one observable is shown on the top left here, but which you should think of as saying it's the observable that says yes, that says yeah, that's what I observe. If the flux density has this figure 8 shaped form with some density, it's just an impressionistic thing. If there's flux of this shape, and now there's another observable that says yes, if the flux is of the form of these two tori, and so then under this Pontryagin product here, you ask for the observable where light cone time runs diagonally here, where the flux density is first of this figure 8 shape form and then of this double donut form. So in this sense, it's like a time order product, but for topological observables, and it's actually light front ordered. And this is a well-known thing. There is light front quantization, and it's also a well-known thing going back to Feynman's thesis from 1946 actually. The quantum operator product is sort of the time-ordered version of the classical product. So that's one way of understanding what's going on. In any case, this algebra exists, and I'm gonna declare that to be my algebra of quantum observables whenever there is sort of this light cone quantization. So wherever spacetime splits of this two-dimensional Minkowski factor, and in the one case where one can actually compute this by more standard means, it coincides. That's what we worked out in this article, quantum observables and quantized fluxes. If you look at G. Young-Mills theory on R11 times the surface, and you use, that's important, one needs to do non-perturbative quantization, not the usual formal deformation quantization, but refill C star algebraic quantization. And then one finds this kind of data actually. Alright, so with our quantum observables in hand, we find the topological quantum states rather easily, or at least the spaces of them. Namely, quantum states, they must be modules over the algebra of observables, obs modules. But here we just saw that our algebra of observables, for the ordinary observables, at least in degree 0, is just the group algebra of a fundamental of a group, the fundamental group of the mapping space. And modules over group algebra are of course nothing but linear representations of that group. So here we find the quantum states form pi1 representations. And these are equivalent local systems on the mapping space. So we conclude here from this little analysis, after we've IR completed our high gauge theory, by choosing this classifying space A compatible with the characteristic and infinity algebra, then its space of quantum states are actually local systems on the mapping space from this lower dimensional Cauchy surface to A. Alright, so just last year there was an interesting argument by Stefanic that concerned exactly such assignments, in our case, to a manifold x d-1 of the infinity category of local systems on a mapping space from that manifold into a given classifying space. And the argument said that these assignments actually extend to extended TQFTs. These are actually the codimension 2 assignments of extended TQFTs. Now, here I want to amplify, we're really just dealing with something like a boundary theory of this, because these infinite categories of local systems, these local systems among them are our state spaces. So the infinity category of all local systems is not the state space, but we need to pick an element in there. And so the actual state spaces are actually transformations, relative field theories or boundary field theories, transformations from the constant functor, the tensor unit here, to this functor of local systems, which pick in each manifold pick such a Hilbert space. And then we just observe that if we really have an extended field theory here, then in particular it extends upwards, and this assignment will actually be a diffeomorphism invariant in the following sense, that if we fix this assignment if we focus on a given fixed manifold and don't consider cobordisms between it, so if we restrict to what is called the modular functor of the theory, just checking what it does to a given manifold, including its diffeomorphisms, then we find that this assignment here of these spaces is a cone over B_diff, right? If you think of B_diff as the infinity group with x d-1 as a single object, and its diffeomorphisms is the higher morphisms, then our H here is a cone over this B_diff index diagram, and as such, such a state is a limit over B_diff of these local systems. But since local systems is equivalently maps to vector infinity, or we can take that limit inside, and it becomes a co-limit over the argument here. So we find that H is actually an element in the local systems, not just of our mapping space, as we had seen previously, but actually of its homotopy quotient by this diffeomorphism group. This is what in physics would be called general covariance of our quantum states. And that is the little conclusion, that is the main little conclusion that I wanted to advertise here. Once you have IR completed your higher gauge theory, choosing a classifying space whose R rationalization is the characteristic of your Gauss laws, then that is the topological quantum spaces you find. And what I want to do now in the remaining time is that I want to indicate that this is actually interesting, because this actually matches local systems that are currently seen in experiments in the real world. This actually connects. This is not fantasy physics, as so much is in the discussion of TQFTs. It is directly related to what people are currently trying to figure out about quantum materials in the real world. So, okay, let's step back. So I'll just throw some buzzwords at you now. If you are actually sophisticated mathematician that I claim this talk is for, you may not have heard of these applications of quantum physics that I'm mentioning now, but I will not explain these either, actually. So maybe my audience shrinks now to the handful of people who are both sophisticated mathematicians and experts on solid state physics. But maybe you can just absorb these terms by osmosis. So there's something called topologically ordered quantum matter. It plays a big role in the hopes of building stable quantum computers, but it's also very interesting just in itself. And here's my way of characterizing these. These are quantum systems that are characterized by some external parameters, p and some parameter space p. And for every value of p, they have what's called gapped ground states, which are Hilbert spaces, so in particular C modules, vector spaces, for each parameter value p. And the quantum adiabatic theorem says that as the parameter p varies, since they are topologically, topological phases, these gapped ground states, Hilbert spaces, will vary along the parameter space in a flat way. They will form a local system. And the actual topological order is actually the isomorphism class of that local system. The representations of that fundamental group, that is the topological order. So here's the archetypical example. If your parameter space is a space of configurations of points in a plane, say defects in some essentially two-dimensional crystal, as shown in the plane on the left here, so you then move in the parameter space, these defects form a braid, and if you have a local system, if you have a quantum system that is kind of parameterized by this, it will adiabatically follow, if you do this slowly enough, along this braid. And if you move through a circle in parameter space, coming back to the original configuration, you will have generated an automorphism, a unitary automorphism for a realistic quantum system of your Hilbert space associated to a given configuration. And hence you find that your quantum states, your ground states, form representations of the braid group, and that's called, when you say, oh, look, we have anionic states. So that's the canonical example of this setup. But specifically, because we want to see this local system mapping space appear, it's very interesting to consider this for what's called crystalline phases. So these are systems where the external parameter space is a crystal lattice, indicated here in this cartoon picture. Suppose you have some crystal, it's defined by certain couplings and some potentials, and so it's actually encoded in the one electron Hamiltonian, in the energy landscape that a single electron sees as it moves through this crystal. So we're not actually, this is important for experts in solid state physics, but we're not actually looking at single electron systems here. We're looking at strongly correlated many electron systems, but I'm pointing out that the parameter space of the system is actually encoded in the single electron Hamiltonian. This is maybe an underappreciated point, but it's kind of obvious once you think about it. And that means actually that our parameter space, by Bloch's theorem, is, because we're on a crystal, is a space of maps from the Brillouin torus, what's called the Brillouin torus, to the set of Bloch Hamiltonians. So there's some kind of Fourier transform going on here that says, oh, okay, if we do have Hamiltonians for electrons in this periodic crystal, then we can actually go to the momentum space. The effective momentum space of these electrons due to the periodicity of the crystal is actually a torus, and called the Brillouin torus, or the Brillouin zone often, but it's a torus. And to each momentum, then we have a Hamiltonian, the Bloch Hamiltonian, that momentum, which encodes the internal, like orbital energy, degrees of freedom, that an electron of that momentum, of that crystal momentum has. In any case, such a map is now what encodes the parameter space. And so, if we call the Brillouin torus sigma for surface, since we're looking at 2D systems mostly, in the space of Bloch Hamiltonians by calligraphic B, that used to be our calligraphic A, then we see the parameter space is mapping space, and so, by what we said before, the topological order of this system is encoded by local systems in this mapping space. And if one concretely does this for already almost the simplest non-trivial case, but which is the one of great practical and theoretical interest, of two-band Chern insulators, of which the celebrated Haldane model is an example, then it turns out the classifying space of these Bloch Hamiltonians is homotopy equivalent to just CP1, it's just a sphere. It's effectively the Bloch sphere. It's just the sphere that arises when we say we have for each electron momentum two states, two bands that the system can be, and then we're picking one. Anyway, it's the sphere, and so we find that the local systems we should be looking at in order to classify the topological order of these crystalline fractional Chern insulators is actually the local system of the mapping space from the Brillouin 2 torus. We're looking at two-dimensional systems, 2CP1, and let's actually quotient of this diffeomorphism action that we found abstractly, and then one can prove. This goes back to a computation that algebraic topologists started doing in 1974, which we kind of revived recently. And anyway, it's a fun little computation using whitehead brackets. One finds that these local systems are exactly representations of integer Heisenberg groups with the root of unity as centers. And whatever that means, if you don't know what it means, the upshot is that these are exactly the anion quantum states, the expected anion quantum states of fractional quantum anionic Hall phases. And I just want to amplify two things. So the upshot is here, this is something actually seen in experiment. So first of all, I want to amplify the fact that we're seeing this root of unity, which means that we're actually in rational, this is what the fractional quantum Hall refers to, that we're actually looking at the rational filling fractions, the Hall liquid. That is actually induced by this diffeomorphism invariance, and then I want to amplify that is actually seen in experiment, which is most remarkable if you think about how this came about. This is a sort of a general covariant effect in topological high gauge theories. In fact, this is 5D Maxwell theory, if you remember that CP1 was the classifying space for the fluxes of 5D Maxwell theory, Maxwell-Chern-Simons theory. So since 2000, these things have actually been measured in experiment. This is the nature article. So this goes back to Nakamura and his group. This is Nature advertising the result. This was in 2000. And so I'm coming to a conclusion now. Just some outlook actually. So above, meaning on top of, energetically on top of the topological sector, these fractional quantum Hall excitations actually are known to have two infrared symmetries. They're both actually seen in experiment recently. One is, it's called W infinity symmetry. This is the Lie algebraic version of volume preserving or area preserving diffeomorphisms, reflecting the incompressibility of these systems. And the other is, remarkably enough, supersymmetry. There's an effect of supersymmetry that is actually seen in experiment between the bosonic and the fermionic excitations of these fractional quantum Hall liquids. And I just want to point out that this combination of infrared symmetries is just the characteristic symmetries of super p-branes. Super p-branes generically have volume preserving diffeomorphism invariance and of course supersymmetry. So this motivates what's called geometric engineering of these fractional quantum Hall phases on M5 branes. So that's really where the motivation for this IR completion of these supergravity theories comes from. We want to ask, can we model these strongly coupled condensed matter systems, for which theory is actually lacking? Everything strongly coupled, strongly correlated is not well described by established quantum field theory. Can we map this though to a system of branes, maybe at some orbifold singularities? This is called geometric engineering. Can we kind of embed it into a more complex looking but more tractable theory of gravitational branes? Understand it there, called geometric engineering. But since we really care about the topological effects here, not just about some transport coefficients, but really the global structure of this theory. These onions are something you can only really understand if you have a global theory. Well, we need IR completions of 11-dimensional supergravity and its M5 brane, such as to provide a global model of the C field, the high gauge field of supergravity, and an M5 brane model. So that's really what drives this theory. It's kind of interesting, I think, because it gives a very clear connection between high-dimensional supergravity and actual experimental physics. And I have here some more slides on how this works. But these are not really done yet. I'll stop here. I'm out of steam anyway. Anyway, the claim is there is an IR complete M5 brane model for the single M5 brane. Really, I should amplify here. Everybody has been talking about what is the theory on coincident M5 branes, which people expect exists, and if it exists, it should be, non-abelian such and such. But overlooked all along has been that even the single M5 brane, which everybody thought is so well understood, has not actually even been fully defined previously, because it was only always defined on a single chart. If you ask what is its global IR completion, you have to specify more data. And the claim is one way of classifying is by using a classifying vibration as a twistor vibration. So anyway, you choose, since it's a brane now, this is what I explained on this slide that I skipped. You need to choose not just a single classifying space, but actually a vibration of them. Twistor vibration is one good choice, and then you can put that on an AN singularity. And this is actually rigorous. So what I'm talking here, often people, when they make these claims about M5 brains and then you dig into the literature, you see it's just folklore. There's no real definitions of these brains. There's no solid math behind it. It's kind of a story. But here, yeah, anyway, so one can actually make full sense of this. And then I claim, and yeah, we've been discussing this in a few articles, that you put these R-complete M5 brains at AN singularities in a particular way. And it actually reproduces fractional quantum Hall topological order in fine detail. Alright, that's it for now. That's the end. Here just again the references that this stuff is based on, if you want to look anything up. And also, of course, I have the links to all these articles and also to these slides on the webpage, which I'm linking below this video. Alright, thanks everybody.